Welcome to e-learning presenting the AKTS-THERMOKINETICS Software, TK. The Thermokinetics Software, TK, permits the evaluation of kinetic parameters from thermoanalytical data. The kinetic parameters allow the prediction of the reaction course at any temperature mode. The software can elaborate the data supplied by all types of thermoanalyzers available on the market produced by reputable manufacturers. The following presentation shows the workflow of the kinetic analysis of DSC data collected in non-isothermal conditions. Enter your password, by default admin, to start the AKTS-THERMOKINETICS software. Import of data. The first stage of the kinetic workflow is the import of data. The computation should be carried out with experimental data obtained at different heating rates. The option, Import Data, allows the importation in text format of any thermoanalytical data independent of its kind. After selection of the data files for further elaboration, one has to specify the properties of temperature and time columns and the type of the measured signals. Finally, the type of signal and an initial sample mass must be introduced. The input of further data of the same type requires only updating the sample mass. After finishing data import, the labels of the curves are visible in the tree view under importations and the required signals can be selected to construct the baseline. One can easily scroll, zoom and pan the chart and its axis with the mouse wheel. The user can display each signal for examination by clicking in the tree view on the row, heat flow, located below the row containing a signal number. Construction of the baseline. After importing the data and displaying them as plots, the next step of the kinetic workflow is the construction of the baselines. The user has to construct two baselines only, generally for the lowest and the highest heating rates, non-ISO, or the lowest and the highest temperatures, isothermal mode. An automatic procedure of the baseline construction can be applied for the remaining curves. The baseline construction starts with placing the cursor on the signal. The cursor icon should switch to a hand symbol, followed by the right click on the graph and selecting the option, Baseline Construction. After selecting Baseline Construction, the window Baseline opens and the type of baseline can be chosen. The correct determination of the baseline course belongs to the most critical part of the experimental data treatment because it influences the evaluation of the reaction enthalpy or the proper dependence of reaction rate and extent on time or temperature. The user can select the baseline from the large set of baseline types. It is recommended to use the tangential sigmoid baseline type for non-isothermal data and horizontal or horizontal last point for isothermal data. After selecting the baseline type, one must choose the left and right temperatures, integration limits, between which the baseline will be constructed. The calculation of the baseline course proceeds automatically. Automatical determination of the baseline course can be optimized manually. Sometimes, a manual adjustment of the tangents is needed when applying a tangential sigmoid baseline type. A double check of the baseline construction is required before continuing because a manual adjustment may be needed. To perform the manual adjustment, one must select the baseline, double-click, and change the tangents at previously chosen low and high temperatures accordingly. The tangents can be only modified if the window baseline is visible. After the final adjustment of the baseline, the window baseline can be closed. After constructing the baseline, the user can evaluate the dependence of the reaction rate and reaction progress on temperature or time. These curves are later applied in the following stages of kinetic analysis. The upper plot shows the temperature dependence of the DSC curve at 8 Kelvin per minute and the baseline construction. The plots show the temperature dependence of the reaction extent, middle section, and the reaction rate, bottom section. The next step is the construction of the second baseline, usually for the curve recorded with the lowest heating rate, in this presentation, 0.5 Kelvin per minute. The baseline construction is performed the same way as already explained before. The red tick placed on the signal represents the temperature of the left limit of the baseline chosen for the highest heating rate of 8 Kelvin per minute. The position of the red tick helps to select the left temperature limit for the signal recorded by the heating rate of 0.5 Kelvin per minute. In general, by increasing scanning rates, the temperature ranges of the reaction are shifted to higher temperatures. Therefore, the left integration limit at 0.5 Kelvin per minute has to be placed at a temperature lower than the signal recorded at 8 Kelvin per minute. Therefore, the left and right temperature limits for the remaining signals, 1, 2 and 4 Kelvin per minute, should be placed between those chosen for the lowest and highest heating rates, 0.5 Kelvin per minute and 8 Kelvin per minute, respectively. For the remaining signals, it means the signals measured at 1, 2 and 4 Kelvin per minute, the option, automatic baselines, is applied to construct the missing baselines automatically. After the automatic construction of the baselines, it is important to check whether the additional manual adjustment is necessary or not. It is necessary to check if the tangents at left and right limits are in line with the signals in constructed baselines. Before accepting the course of the baselines, it is also necessary to check if the standard deviation of the reaction heat determined at all heating rates does not exceed 10%, because higher deviations may indicate poor data quality or incorrect baseline construction. After checking the correctness of the baseline constructions, the user can begin the kinetic analysis of the recorded data. Evaluation of kinetic parameters. The evaluation of kinetic parameters by differential isoconversional analysis starts after choosing the tool Kinetics. In the first step of the kinetic analysis, the plot showing the dependence of the reaction progress on the temperature at all heating rates is created. The standard deviation of the reaction heat determined at all heating rates should not exceed 10%, because higher deviations may indicate poor data quality or incorrect baseline construction. The reaction extent can also be displayed as a function of time. The reaction progress can also be expressed as a time or temperature dependence of the evolved heat of the reaction displayed in joule per gram. In the second step of the kinetic analysis, the plot showing the dependence of the reaction rate on the temperature at all heating rates is created. The reaction rate can also be displayed as a function of time. In the third step of the kinetic evaluation, the logarithms of the reaction rates are presented as a function of the reciprocal temperature for the different heating rates. In the differential isoconversional analysis, the slopes and intercepts of the lines drawn through the isoconversional points at which the values of the reaction extents alpha are the same at different heating rates enable the determination of the kinetic parameters. The dependence of the activation energy E on the reaction extent alpha is displayed in red. The reaction extent dependence of the term containing the pre-exponential factor is displayed in blue. The black curve shows the dependence of the correlation coefficient on alpha. For a better presentation of the dependence of kinetic parameters on the reaction progress, one can move the position of the curves using the option Adjust Axis Vertically by placing the cursor on the respective command in the panel and right-click. The construction of the baselines influences the results of the kinetic analysis. In AKTS-TK software, two criteria must be fulfilled to evaluate the meaningful kinetic parameters. As the first criterion, the average correlation coefficient R of all straight lines plotted in isoconversional coordinates should amount to at least -0.99. In the second criterion, the standard deviation of the values of the reaction heats determined at all heating rates should not exceed 10%. The user should always try to improve the baseline construction manually. In case of an incorrect, illogical baseline, it makes no sense to start the automatic adjustment because the construction is too far from optimal. Improper construction of the baseline for the DSC curve recorded with a heating rate of 8 Kelvin per minute results in unacceptable R values and standard deviation of the reaction heat. The current figure shows the case when both criteria of the proper baseline construction are not fulfilled, as indicated by the warnings displayed in red. Improper baseline construction for the signal recorded at a specific heating rate, here 8 Kelvin per minute, which is not consistent with other baselines, influences the course of the dependence of the reaction extent on temperature, which results in improper kinetic data. Warnings are displayed for deviations larger than 10% if criteria 1 or 2 are not fulfilled. Optionally, the user can try to improve and optimize the construction of the baselines by using the corresponding baseline optimization tool. Automatic baseline optimization slightly changes the tangents at the left and right limits for the signals recorded at all heating rates. This improves criterion 1, R value, by achieving a value closer to -1. If the R value after manual adjustment is already close to -1, the user can skip this option. Simulation of the reaction course. After baseline optimization, the new kinetic parameters are calculated and used to simulate the reaction progress for all measured heating rates. The simulation procedure starts after choosing the tool, Simulation. The thermoanalytical peak, for example, the signal of a heat flow rate as in the case of DSC, is placed between the points of departure from, left limit, and return to the baseline, right limit. The proper choice of these points significantly depends on the thermoanalytical device's sensitivity and the measured signal's shape. The temperature of the reaction beginning increases when the heating rate increases. Often, the beginning and the end of the departure of the recorded signal from the baseline are not well defined. Therefore, reliable information concerning the reaction course is generally possible only in the range of alpha between 0.01 and 0.99. Optimization of kinetic parameters. The additional improvement of the prediction of the reaction course can be achieved after optimization of the kinetic parameters. The tool, Optimization, opens a pop-up window allowing optimization of the kinetic parameters. The optimizing procedure starts by choosing the Optimize tool. In general, 100 loops are enough to achieve a good fit between simulated, black, and experimental, colored, signals. In case of any doubts, the user can repeat the optimization procedure or undo it. If both criteria, R value and standard deviation of the reaction heat, are fulfilled, the user can expect a good fit of experimental signals by simulated curves. If this is not the case, further optimization is needed, which means more optimization loops than 100 are necessary. After adjusting the kinetic parameters, the simulation's black curves fit the experimental reaction course much better. To finish the optimization procedure, the user should close the optimization window. After optimization, the courses of experimental and simulated curves can be displayed as a function of temperature or time. Before closing the kinetic analysis, one should save the results in Kinetic project file equals KPF file. The kinetic data can be saved using the Save Kinetic project tool.